Wait,
Sure. Sarah will come at the end of the lecture. Produce. Oh, okay. She'll take a picture and then. Is it okay? Yeah. If you want, I can do then all the announcements. Whatever. Okay. Yeah, I'll come back. Okay, I can do it.
Here are the things people need for dinner.
Okay.
We still have to count, but maybe close to 10. Cool.
guys know this stuff.
And then for the, how does it work for the network?
I want to just grab people.
We just grab people. Mark, let's say.
Thanks for doing this.
Sure.
How's it going?
Good. Yeah. It's nice to be on summer.
Give Jordan's.
Yeah, off and on, yeah. For sure. Be here most of the time.
Best time of year.
It's best of the year.
Okay. Welcome back, everybody, to this afternoon session. Before I introduce the next speaker, a quick announcement. After this talk, we'll have a group photo. So in case you want to fix your hair, you still have 1.5 hours for that. We'll take one inside. We'll probably also take pictures in the botanical garden, given that the weather is nice now. And then after that, there will be a lab tour that actually Tiancheng will lead you to. And the lab tour is actually fitting to the next talk. So it's a great pleasure to introduce Mark Saffman, who is a really world-leading expert in what he's going to tell us about. AMO physics applied to quantum computation. And the lab tour will be in his lab. So Mark, it's a great pleasure you're here. And the stage is yours.
Okay, thank you, Leo. Maybe that's a little loud. How's that? So, good to be talking to you. You've already had a day and a half of talks about quantum computing, and I guess you all know quite a bit about quantum computing. So today I want to talk to you about the neutral atom approach to quantum computing. And the department here is one of the places where this approach was pioneered. So we've been working on this a long time, and I'll be happy to tell you about it. What I'm going to do is sort of, I mean, it's a lot of material in principle. I could talk for days about this topic, but I'll try and pick out some important aspects, and I want to also give you some introduction to the underlying microscopic physics, that is the atomic physics that goes into using atoms for quantum computing, And towards the end, I'll get a little bit more into architectures and what people are thinking about in terms of building quantum processors and quantum computing machines using atoms. And I'm very happy we can make this interactive, so please don't be shy about shouting out any questions or interrupting me along the way. Okay? All right. So neutral atom quantum computing, and for full disclosure, there we go. I'm here in the department. I also spend some of my time working with the inflection company who's working to commercialize this technology. Okay, so this is my research group recently, and we're working on quantum computing. This is not a great pointer. Let me take a different one. It sort of seems not to work half the time. I have another one here. That's better. Yeah, okay. We're working on quantum computing, quantum networking, and also quantum clocks in my group. I'm just going to talk about the computing. I'm happy to emphasize in this day and age that we're a very international group. We're actually 10 different countries working with us here in Chamberlain Hall, which is a lot of fun. Okay. So there's also lots of places where you can find background information in the literature. Here's a couple of reviews that I've listed. Some we wrote, some other people wrote. I'll be self-promoting. I mentioned that in this second edition of this book that I co-authored, there's a whole chapter on atomic qubits. So you can also find more background info and also a lot of useful references in that chapter. Okay. So, quantum computing, there's many ways you can think about developing a quantum computer. There's a handful of platforms, I'd say 5, that are really attracting the bulk of the effort these days, both in terms of academic groups, but also commercial investment in the technology. And I guess you've already heard about quantum dots, or that's coming. You've been hearing about superconductors. So in this department, we have active efforts on superconductors, quantum dots, and neutral atoms. Not so much on the other two. And all of these platforms have a history. And here I just kind of indicated that timeline in terms of when was the first 2-qubit gate demonstrated, and it was first on entrapped ions. And then the second number I've listed for each platform is when that platform was able to start running circuits. And by circuit, I mean that you had more than 2 qubits, and you had more than one gate, and you're doing some kind of computation. And it took some number of years for each of these platforms. Neutral atoms were actually the last one to demonstrate a 2-qubit gate, and also the last of these to demonstrate a circuit. But the rate of progress has been very substantial lately over neutral atoms. And you can see that progress in terms of gate fidelities, which have surpassed 3 nines for both trapped ions and superconductors. And qubit counts that are actually used in circuits are also over something like 400 in superconductors. But in principle, all of these approaches will eventually be a very useful quantum computer, but the devil is in the details. And then there's also a lot of companies working on these things. I work with Inflection. I guess I should add Collab to this list here. But there's worldwide, I keep a list, there's something like 50 companies working on the hardware of quantum computing, and probably a couple hundred working on software. So there's lots of people trying to do this. Okay, so what is a neutral atom qubit? So here's an example of an atomic structure that can be used for making a qubit in quantum computing. And I want to start with one slide that just in a nutshell gives you an overview of what the basic idea is and why we think neutral atoms are an interesting way of approaching quantum computing. So what I'm showing here is the ground level structure of the cesium atom. So cesium has 1 valence electron, spin 1/2. There's a bunch of core electrons, but they're in filled shells, and so we can ignore them. There's 1 valence electron, which interacts with the nucleus, which has a spin of 7/2. And so the interaction, the hyperfine interaction of that valence electron and the nucleus gives you total angular momentum of 3 or 4. So that's the F quantum number. And each of those levels has 2F plus 1 Zeeman substates, which we label with the quantum number M. And so we choose these two states with m equals 0 to encode our qubit, which has a frequency of 9.2 gigahertz. And I like to refer to this as an industry standard qubit, because the energy or frequency of that transition is today the international definition of the second. So that's about as standard as you can get. And it's exactly that transition which defines the second that we also use for our qubit. And these ground states, these atoms are very small, they're tiny, they're electrically neutral, they interact weakly with the environment, they have very good coherence properties, and they also interact very weakly with each other. So if I have two of these atoms in these ground states, even just a few microns apart, they almost have zeros in interaction. It's sort of a few parts in 1,000 of 1 hertz. So they're very weakly interacting, makes a very good quantum memory. Okay, so it says superb quantum memory, but we want to do quantum logic. We want to do computation, so we need interactions between the qubits. And the way we enable interactions is we shine lasers at these atoms, and we promote them up to these highly excited atomic orbitals, called Rydberg states, where the atom becomes, the wave function becomes much larger, and the interaction strength between two of these atoms increases by a ratio of about 12 orders of magnitude. So we have this coherent mechanism using laser pulses of turning the interaction on and off with a contrast ratio of 10 to the 12, which is kind of remarkable. And that lies at the heart of how we implement fast quantum logic and why this is a good system for quantum information. Okay. So that's sort of a very quick intro, and then I want to go through a few topics. I'll tell you in some more detail about the atomic physics underlying the use of atoms as qubits. I'll tell you about the Rydberg interactions, how we do gates, and then architectures. And if I get too far behind, I'll try and speed up so we have time for this stuff at the end. Okay. So here's again this qubit encoding in the clock states, what we call the clock states, the m equals 0 states of the cesium atom. And that's the frequency between those two states. And so you can ask, well, if I encode a quantum superposition of those two states, how coherent will it be? How long can I maintain that superposition? And that's important. We want to reduce the decoherence rate in order to reduce how much error correction we have to do computation. So there's sort of a background limit, which is just the black body-induced rate of transition between those two states. And if you take one of these atoms and just put it in a room temperature environment, it will transition with a characteristic time constant of about 35 years. It's much longer than a graduate student lifetime, typically, so don't have to worry too much about that. But if you have many thousands or millions of these atoms, even if everything else was perfect, you would care about that number. So you want some error correction. Okay. In practice, what really sets the limit on coherence is magnetic fields. So although these are m equals 0 states and have 0 linear Zeeman shift with magnetic field, there is a quadratic shift with an amount given by this expression here. And there's also an intensity-dependent clock shift. That is, we will do laser cooling on atoms and then trap them in optical tweezers, which are basically just focused laser beams like this, focused down to a small spot. And when we do that, the two states respond slightly differently to the optical intensity, and they give which will give a position-dependent or intensity-dependent energy shift as the atom oscillates back and forth in the trap, and that also leads to decoherence. And if we sort of look a bit more broadly at what's going on with these atomic qubits, there's a couple different energy scales that come into play. So there's the qubit, and in cesium, these two levels are separated by about 9 gigahertz. And then we apply optical fields to trap them in tweezers. And I'll talk more a bit later about how that works. And that optical frequency is hundreds of terahertz. If we zoom in on the qubit separation, that's some gigahertz. And then in an optical trap, these levels are confined in an optical potential. And if we zoom in at the harmonic oscillator spectrum of that potential, we see oscillation frequencies or motional normal modes, vibrational frequencies of the atom that are measured in kilohertz to megahertz, typically tens of kilohertz for neutral atoms in optical traps. And then, because these two levels respond slightly differently to these optical frequencies, there's some differential shift of those levels that gives decoherence, and that's generally sort of kilohertz. So we have energy scales in this problem ranging from kilohertz to megahertz to gigahertz to terahertz, so a very broad spectrum to keep track of. And the limitation on the coherence time, or the inhomogeneous relaxation time, the T2 star, depends on the temperature of the atoms, which determines how much they're moving around in the trap, and this differential light shift, which depends on the relative interaction of those two states with the optical trapping field. And one can derive, it was done a long time ago, an expression for the coherence time as a function of that differential light shift and the actual temperature of the atoms. And so one can kind of look at what that's going to be using laser cooling techniques. I don't have time today to go into much detail or any detail about laser cooling, but there are very well established methods for reducing the motional temperature of the atom down to a few microkelvin or even hundreds of nanokelvin. And when you do that, and say with typical trap parameters, you can have T2 star times that are tens of milliseconds, so 0.05 seconds, for example. And using dynamical decoupling, it's now pretty routine to see coherence times of several seconds. So we have very, very coherent qubit encoding. Okay. So let's see, I've taken 15 minutes. I think I'm going to skip over this, which goes into more details about these traps. I'll just briefly say that there's this decoherence mechanism from the atom moving around in the trap. There's also a decoherence mechanism, which is those two levels respond slightly differently to magnetic fields. So any background magnetic noise from the elevator or an air conditioner or any electrical appliance will contribute to decoherence. There's ways of engineering the frequency of the trapping light and adding additional frequencies to simultaneously cancel that intensity-dependent noise and the magnetic noise. And it sort of gets into a lot of atomic physics details, but I'm actually, it's kind of interesting for me, but I'm going to skip that and move on to talk about which atom we should use. Okay. Let me just stop there. Any questions about the basic idea of encoding a qubit in states? Okay. So here's the periodic table. The colored elements are atoms that have been laser cooled, so quite a few of them now. And then there's a subset of those elements that are being used for quantum information. It's primarily, for neutral atoms, primarily the heavy alkalides, rubidium and cesium. There's some work in lithium, not so much. And then in the last 5 years, strontium and ytterbium have become very popular. They have a more complex internal structure, which gives them more sort of tools in your toolbox. And then there's also the lanthanides here, which at first sight appear to have a more complicated structure and have not yet been used for demonstrating quantum gates, but might well turn out to be very interesting atoms for this application. We'll see. And when we work with these atomic qubits, there's no fab. We think of a new way of doing things or a new experiment we want to try. we don't have to fabricate new qubits, right? They're natural qubits, they are what they are, they're nature's perfect qubits, and the challenges and competitive differentiators are really about the architecture and the ancillary technologies. The vacuum, the lasers, the optics, the control stack, software for lasers. And so, you know, we can make 1 million cold atomic qubits very easily. The challenges are all in the associated things. So here's two of the most popular atoms, they're cesium and rubidium, and they both have a ground hyperfine structure, and then slightly different wavelengths are used for cooling, but sort of the same encoding idea where you use two of these hyperfine states. And now there's also the alkaline earth atoms. Strontium and ytterbium are widely used. Let's see, it's just to turn off the captions here. Right? I can't do that probably. And in these alkaline earth atoms, you actually have additional encoding possibilities. If you're using an isotope, the nuclear spin, so the ground state of these alkaline earth atoms is I didn't write it here, it's a spin 0 state. These are 2 electron atoms, 2 valence electrons, and the ground state is a spin singlet with 0 angular momentum. But if the nucleus has spin, then you can encode a qubit in the nuclear state, so 2 different M states within the nucleus, and that's very well protected from the environment. And then you have a singlet series, which is generally used for laser cooling, and then a separate triplet series, which the lowest lying triplet levels of these atoms are triplet P0, 1, and 2, different angular momentum. And there's 3 different ways people are exploring qubit encoding in these alkaline earth atoms. One is in the nuclear spin qubit. The second method is to use this excited triplet P0 state, and it's electronically excited with a wavelength that's typically sort of invisible here. But you're still encoding in the nuclear spin, but you're just in an electronically excited wave function. And the lifetimes here can be hundreds of seconds. And you know, I said this is the current international standard of the second in cesium, this transition. Well, this transition in strontium will, in the next few years, I think, replace the cesium atom as the international definition of the second, because it's a much more accurate clock because it's a higher frequency. But you can encode down here, you can encode up there, you can encode a qubit where one state is down here and one state is up there, so an optical frequency qubit. Actually, there's 4 encoding methods. There's also a couple groups in Germany looking at encoding in these 2 different metastable levels, which has a frequency in terahertz, so it's a fine structure qubit. So there's a bunch of different encoding options in these alkaline earth atoms, but I'm going to mainly concentrate on the alkaline atoms. Okay. So atomic energy levels, you know, this was worked out a long time ago. Rydberg published his formula in the late 1800s for the wave numbers of spectral lines, and so we have this very compact formula in terms of the Rydberg constant R, the principal quantum number, and so-called quantum defect for what the energies are at the nth level. And we can relate that Rydberg constant to fundamental constants, as you learned about in introductory physics. But we're going to use these Rydberg atoms for implementing gates, so we want to look a little bit more closely about how things work. So Rydberg's formula applies universally for determining atomic emission and absorption spectra. And in modern usage, the term Rydberg atom has come to mean a highly excited atom with a large principal quantum number n. So stop up here. You might ask, well, how large does n have to be for an atom to be considered a Rydberg atom? There's not a tight definition. Dan Kleckner, who did a lot of pioneering research on Rydberg atoms in the 70s and 80s, I heard him say n greater than 10 is a Rydberg atom. So So almost all states are Rydberg states. But for quantum computing, we like to use states pretty far up, and the reason is that the properties become exaggerated in ways that are very beneficial for quantum information. So as we go to highly excited atomic states, the size of the wave function, or the radius of the wave function scales as n squared. So the size scales as, the area scales as n to the fourth. But in addition to that large size, the lifetime, maybe counterintuitively, scales as n cubed. Not counterintuitive if you think about it a bit more, but you get higher and higher excited, you actually get a longer lifetime. And so if I go up to the 100s state, so 0 angular momentum, n equals 100, in a room temperature environment, I have a lifetime about 300 microseconds. That's about a 2 micron across wave function. And you can also think about preparing states with the maximum possible angular momentum. So these are the states with L is n minus 1. So this, sorry, not 100s, but n equals 100 state with L equals 99 and maximum projection of angular momentum, m is 99. That wave function is a torus. Looks like a donut. And similar size to the low angular momentum state. It's a little bit more compact. But it has a lifetime of cryostat of about a second. And as you'll see, we do quantum gate operations on these neutral atom qubits in microsecond or sub-microsecond timescales, so we can get very long lifetimes compared to gate operation times with these Rydberg states. Okay. So how do we excite these Rydberg states? In the alkali atoms, traditionally, almost all the experiments have been a 2-photon excitation, where we start with a, for example, a blue photon, and then an infrared photon, and in the 2-step ladder process, we go up to the Rydberg state. In cesium or rubidium, same kind of idea, slightly different wavelengths. Or you could think about 1 photon from the ground state to the Rydberg, which would be in the UV. That's not being explored so much. We're currently upstairs working on doing this 1 photon excitation in cesium with this 320 nanometer light. And then in the alkaline earth atoms, essentially all these qubit experiments have been starting at this metastable state, which, as I said, has very long lifetimes, hundreds of seconds, doing 1 photon up to a Rydberg state for strontium and ytterbium. You know, accidentally, the wavelength for strontium from P0 to Rydberg is about the same as cesium from the ground state, and for ytterbium, the wavelength is close to the ground Rydberg rubidium wavelength.
How do you swirl up your atoms to get m equals 99?
Yeah, that's a good question. So I need to, if I want to get up to m equals 99, I have to add 99 units of angular momentum. And each photon only adds 1 unit. So what they do is they go from the ground to, say, L equals 1 or 2 optically, and then they do a whole bunch of microwave transitions to add all those additional photons. And people have now demonstrated getting up to these circular donut states in a couple microseconds with fidelities close to 100%. So techniques have been developed that make this possible. Okay, that's just a little technical detail about how much power you need and how fast you go. I'll skip that. And we like these Rydberg atoms for quantum experiments because they have very strong interactions with electromagnetic fields and strong interactions between the atoms, so we can perform gates. Here's a plot of how these states interact with external fields. So here I'm plotting the energy of different states versus an external electric field. And you see that's the S state, these are P states, these are D states, and then for angular momentum beyond D, the quantum defects are very small, and so we get this span of essentially hydrogenic energy levels. It looks just like a hydrogen atom So there's this huge set of states out here. And although the atoms interact very strongly with each other, which we like for doing quantum logic, there's also a challenge in that when we go to these highly excited states, they interact with background DC fields very strongly also. And so the polarizability of the atom giving energy shift scales like n to the 7th. So it's a very fast scaling. So as we go to high n, we have a challenge in that we need to stabilize background fields very precisely in order to have a stable experiment. You could turn that around and say, well, that's going to be useful for field sensing, which it is. And people also use Rydberg atoms for sensing electric fields. And maybe I'll just say a couple words about this. If you look at these states, for example, this p state, it curves down. And that means it's got a positive polarizability. The energy shift is minus the polarizability times the field square. These are quadratic shifts. These d states curve up, so they have the opposite sign of polarizability. And if I want to prevent this state from being sensitive to electric field, if I mix in a little bit of this d state, I can actually cancel out that curvature. And that's something we did in an experiment a couple years ago by Juan and Ravi, where we excited a p state using 2 photons and then mixed in a little bit of a neighboring d state. And we're able to show that we could go from a stark curve, a dependence of energy on the field to look like this, to something that was much flatter, so about 80% reduction. Actually, some of these techniques are getting folded into our quantum computing experiments these days. Okay. Let's see how I do that. Okay, so a little bit more about atomic physics. If we think about interactions with AC fields or optical fields, transitions between atomic states can be controlled with light that has the photon energy equal to the energy between states. So that's, for example, how we go from the ground to an excited state. And states with sort of neighboring angular momentum can couple with each other, driven by allowed dipole transitions, say S to P, P to D, and so on. And those states will have different characteristic wave functions. The strength of the interaction is very large for Rydberg states. Say I excite some NS state here, and I ask about, or NS state here, ask about the coupling to a neighboring NP state. The matrix elements describing that coupling scale like n squared because the wave function has a size n squared. And so I get Rabi frequencies coupling those atomic levels that scale as the electric field amplitude times n squared, and then it's big. I get a very strong coupling. Now, if I think about engineering an interaction between 2 Rydberg states in order to implement a quantum gate, if I just excite 2 atoms to the same state here, what can happen? Well, each of those atoms can couple to a neighboring state, say an NP state, and there'll be a strong coupling, but the energy of those 2 states summed up is different than the energy of those 2 states, so it's not a resonant process. And so it's suppressed because of that. However, what can happen is that the possibility of coupling induces an oscillating dipole between those states, and so one can have a allowed interaction where one atom goes to a neighboring state that's a little bit higher in energy, the other atom goes to a neighboring state that's a little bit lower in energy, and that's an almost resonant process because this splitting here is almost the same as that splitting there. The difference scaling is 1 over n cubed. And so, let's see if I can get to my small animation here. So you get this, what's called a Förster resonance, where things hop back and forth in that way. And that's essentially what's going on when we have a strong interaction between 2 Rydberg atoms in the same states. And so this kind of interaction was first observed in not laser-cooled but thermal gases many years ago, 1981, by Serge Roche, who went on to win a Nobel Prize for work on Rydberg atoms, and they looked at the spectrum depending on the density of the Rydberg states and saw this broadening, which was due to these interactions. That's a dramatic example of the enormous scaling factors existing between the physics of Rydberg and ordinary low-excited atoms. Okay. So, putting all of this together, what one gets is that when the atoms are close together, where the dipole, transition dipole's interaction strength is greater than this small residual energy mismatch, you have essentially a resonant dipolar interaction that scales as the principal quantum number to the fourth power divided by their separation cube, so 1 over r cubed. And if you go to very long distance, you get an effective van der Waals interaction, which scales as a very high power, the principal quantum number, and then 1 over r6. So the interactions are 1 over r cubed at short range, 1 over r to the 6th at long range, and there's a characteristic crossover distance. Okay, so here's some quantitative values. These curves are the interaction strength of atoms in the ground state. There's a background van der Waals, but the interaction is dominated by a magnetostatic dipole interaction between the electron spins for alkali atoms. That's 1 over r cubed, but very weak. And if I go higher and higher in Rydberg principal quantum number, I get these curves, which are 1 over r cubed at short range, 1 over r6 at long range. You can get many megahertz of interaction, in this sort of alpha 5 micron region, and even at 20 microns, I can get about a megahertz. And it turns out for high fidelity entanglement between two atoms using this Rydberg interaction, we now know, in principle, how to do this with, say, 3 or 4 megahertz of interaction strength. So that means we can entangle atoms out to close to 20 microns of separation, which is interesting for architecting these systems. Okay, so I've gone into a fair amount of detail with this, but I want to give you some background about what's the underlying atomic physics. Okay. All right, one more statement about this. If you think about what's going on here with this sort of hopping mechanism, this atom is interacting, there's interactions between different states in this atom, and there's interactions between different states in this atom, but those atoms could be very different atoms. It could be an atom and a molecule. It could be one rubidium atom and one cesium atom. They don't have to be the same type of thing. And so one can also choose particular quantum numbers, particular states, where you have resonances where that energy is exactly equal to that energy in the other atom, and that gives you very strong interactions. And this was shown just last year at the Burning group in Chicago. They entangled the rubidium and the cesium atom using this kind of mechanism. And that's one of the things we're thinking about in terms of building up quantum computers. All right. So to summarize, there's this very strong polarizability that goes into the 7th, which can be a challenge to stabilize. There's very long lifetime, which you can think of as an AC coupling, which scales as n cubed because the energy difference between neighboring states goes as 1 over n cubed. And there's a Rabi rate or atom-atom resonant coupling that goes as n to the 4th or n to the 11th in these two different regimes. So it's very exaggerated properties. Okay. Okay. So I sort of very briefly mentioned that we trap these atoms in optical traps. If we're exciting the atoms to these Rydberg states to do logic, to do gates, probably would be a good thing if we could also trap the Rydberg atoms so they don't fly away during the gate. Turns out the gates are so fast that even if we turn the traps off during the gate, the atom sticks around and we can turn the trap back on. But there's reasons to want to also trap the Rydberg atoms. And it turns out that's possible. We can put atoms in bottles of light and trap them. And to understand how that works, I'll just say a little bit more about light-atom interactions. If I have an atom with some internal transitions, and I shine light at it that's close to a resonance, the atom will absorb photons and then re-emit them in a random direction. And on average, the atom will be pushed in the direction along the direction of the incident laser beam. So that's what lies behind sort of standard laser group. And so I get a force that scales with the rate at which I scatter photons, which scales as 1 over the detuning squared. If I instead take light that's very far detuned from that atomic resonance, I don't get much momentum transfer, but I get an energy shift of the atom, which can be positive or negative. And you can think of that as a pendulum that you drive. If you drive it above or below resonance, you get motion that's in or out of phase with the drive, and that corresponds in the atomic setting to if I shine detuned light at a higher frequency, I get a positive energy shift of my ground state, and if I shine detuned light at the atom where the light has a lower frequency than the atomic transition, I reduce the energy and can make it trap. And so depending on the color of the light I'm shining at the atom and how I shape the light in space, I can make different types of traps. And so the simplest trap is an optical tweezer, where I just take a laser beam and I focus it to a little point, and so I have a localized maximum of the intensity that gives me, for red detuned light, a reduction in the energy, so I create a conservative potential wherein I can trap the atom. These localized potentials are almost perfectly conservative. And so if I had an atom out here and it encountered one of these optical tweezers, it would just roll in and roll out again. It wouldn't stick there. So to actually trap the atom, you have to cool it into that local potential. And that's sort of the most popular way of trapping atoms. But you can also do something a little bit different, which is use some optics to make an optical bottle. So it turns out it's possible. You need more than just a single lens. You need some additional components, but it's not hard. You can make a dark spot surrounded by light in all directions. And we call that an optical bottle. And if you do that with light that is blue detuned and repulsive for the atom, once the atom gets inside the bottle, it cannot escape because it would have to climb the walls to escape the trap. And so it turns out for the Rydberg states, the light is always repulsive because the Rydberg state is essentially just a free electron far away from the nucleus, and those free electrons with negative charge have a negative polarizability and are repelled by the light. And so I can trap both ground state atoms and Rydberg atoms in these optical bottles. And because the atom is trapped where the light is very weak, it sees less decoherence from noise on the trapping light, which is nice. And so, you can also design this very carefully such that the trapping potential for the ground state atom and the Rydberg atom, even though the wave functions are different sizes, have exactly the same depth, and so you get what's so-called magic trapping. So you become, the transition from the ground state to the Rydberg state becomes insensitive to any small variations of the trapping light, which is also a nice feature. So let me not dwell on that too much. We did an experiment. Siwan did this in her thesis, showing that we could do this kind of magic trapping and trap the Rydberg states, and it was also done by a French group in video. And then, so over the years, here in Madison, my groups, one of the things we've done a lot of is develop different ways of making arrays of these bottle traps. And so we started 50 years ago making a single bottle trap, and then different ways of making larger and larger arrays. And so most recently, we did an array of more than 1,200 of these bottle traps in a 2D grid, and we're able to trap a big array of cesium atoms. So you can think of that as a prototypical setting for making a large qubit array in a quantum computer. We didn't run circuits on 1,200 qubits, but we were able to show that we could put in place 1,200 atoms, which could be used as qubits.
I have a question.
Uh-huh.
How far off do you think that is from being used as like having
Yeah, so I'll skip this and just, I'm going to go on to, this slide. So there are many groups making these arrays of traps now around the world. And the most recent results are that a number of groups have shown arrays with more than 1,000. I showed you this one with 1,200. The biggest array that's being shown to date is 12,000 sites with 6,000 atoms. And they have demonstrated global qubit control. So each one of those atoms is a qubit, and they've demonstrated global control of all 6,000. But one of the limitations is actually the optical technology. And the wiring here is not electronic wires, it's beams of light. And so to individually control and wrap the different qubits and do different things at different times and switch back and forth at a very fast rate, you need some optical beam steering technology that doesn't really exist today. We have devices that can switch very rapidly between different locations, but only a few locations. And we have devices that can switch between many different locations, thousands or millions, but they're quite slow. And so we don't have the ideal device available today, but this is something that is being developed. And the largest experiments where they're actually doing qubit control are work from France, work from the Lucan group at Harvard. These are about 300 atoms, is sort of the record right now. I think we're going to see that increase pretty quickly in the next year or two to getting up into the thousands. But I should just back up a second and emphasize that one of the sort of technical hurdles that had to be overcome, I'll skip that, about 2 species, had to be overcome a couple of years ago, is how you actually put the atoms exactly where you want. Because you make this array of traps, and the way you load atoms in is you do laser cooling, and so you have a cloud magneto-optical trap with cold atoms, and then you overlay this regular pattern of traps, and then it turns out you can get some of the traps stay empty, and some of the traps get 1 atom, some of the traps get more than 1 atom, and you get rid of those, but you don't have 100% filling. And so what people figured out, this was in 2016, Korea, Harvard, and Paris, that you could then take a picture, see where the atoms were, and then use another tweezer to grab atoms and move them around and sort of one by one put the atoms exactly where you wanted them. So you could fill up the arrays or make different patterns, and this was even shown to work in 3D in Paris where they made this atomic Eiffel Tower, which is really amazing, I would say.
How exactly do you generate those kinds of potentials with a really deep well in one spot and nowhere else?
How do you do it?
Yeah.
So if you think about, it's really by interference. So you're asking how I make the bottle traps?
Yeah.
Yeah, so supposing I take two of this kind of laser beam, which are bright beams, and I make, I'll just draw the board here. Supposing I have a laser beam like this, where that's intensity, and then I have another beam which has the same peak intensity, but is wider, okay? If you think about taking that beam minus that beam, I'll get a profile that looks like that. Okay? So they have the same peak intensity, so if I subtract the electric fields in the middle, they'll cancel, but because this beam is wider, out here it's stronger, so I get a non-zero intensity. So you can do that in 3D with an interferometer and make a 3D bubble beam. That's one way of doing it. Okay, so now these techniques have become quite sophisticated, and people can make arrays of thousands of atoms that are completely filled. And even having done that, you still have the issue that the atoms get lost because the vacuum cells in which we hold these atoms are not perfect, and so there'll be some density of background molecules that are untrapped, that have bounced off the walls of the cell and are at room temperature, and if they hit one of those trapped atoms, they can kick it out. So there's a vacuum limited lifetime. It can be as long as several hours, but it's not infinite. And so we've started to see, just in the last year or so, experiments where people have these arrays of atoms, but also have neighboring reservoirs of pre-cooled atoms, and they continuously monitor and refill any lost atoms, so you have these continuously occupied arrays. And I think neutral atoms are a great approach for making these qubit systems. They also have some unique challenges. One of them is atom loss. It's not a fundamental showstopper, I would say, but it sort of adds to the engineering pain of actually scaling up these systems and making them useful. And so I think every technology has their own engineering pain. We don't need dilution refrigerators, which is a good thing, but we have some other challenges like this that have to be dealt with. Okay, so that was a lot about atoms and some about atom optical field interactions. Let me go on to talk about the actual gate operations and doing quantum computing. So, the gate set that we've been using in my group is the following. So I'm going to use cesium atoms encoded in clock states. We can drive global rotations with microwaves. So we turn on microwaves that are resonant with that transition. The wavelength of a 9.2 gigahertz microwave is 1.5 centimeters or so. These arrays, the atoms are typically spaced by a few microns. So even for a big array, the atoms are localized to much less than a microwave wavelength. And so just turning on resonant microwaves, I can globally drive transitions on all the atoms in parallel. And by varying the phase and the duration of the microwave, I can drive rotations about an axis in the xy plane of the Bloch sphere that has any angle phi, say, with the x-axis. So I can do arbitrary sort of xy microwave rotations. And then combining the microwaves with focused laser beams, as I'll show you, we can do arbitrary rotations on single qubits. And then using Rydberg interactions, we can do native CZ gates. And then combining that with local Hadamard, we can do CX gates. You can also do multi-qubit gates with the Rydberg interactions, such as the Foley gates, or even larger numbers of qubits in the multi-qubit gate. So here's some old data where we had a 49-qubit array. We turn on the microwaves, they all oscillate back and forth, and sort of out of the box, you get close to 3 nines of fidelity based on benchmarking. The current record for, so this was 2015 or so, the current record is just shy of 5 nines. People have made the microwaves more stable and so on. This works very well. This was not super fast. We now do this. We have bigger amplifiers. We're about 100 kilohertz. So you can drive pi pulses at a few microsecond timescales. So reasonably fast and high fidelity. To do localized single qubit gates, we take a near resonant laser beam and focus it down to hit, say, a single atom at a time, or several atoms at a time, if you like. And then by combining that single focused laser beam that gives an RZ rotation, we can synthesize RX and RY rotations. And the way we do that is we put this optical pulse in between 2 global microwave pulses. And we make the global microwave pulses be, for example, pi by 2 pulses with opposite phase. So if I do a microwave minus pi by 2 and then plus pi by 2 about the same axis, that has net effect of the identity, doesn't do anything, but if I put in between an RZ rotation with a focused laser beam, you can multiply out the matrices, you'll convince yourself it gives me an RX rotation, or if I change the phase here, I get an RY. So combining the global microwave with local optical addressing, you can get local X and Y rotations also. So that's our single qubit gate set in a nutshell. There's other ways too, but this is the way we typically do it. And then we need the entangling gate, and the idea there is to use Rydberg blockade. So, Coulomb blockade is just very naively, if I have a wire and it has a very narrow cross-section somewhere, then because the electrons repel each other, I can only push one electron through at a time. So that's Coulomb blockade. And there's an analogous effect with atoms, with Rydberg atoms, that is now called Rydberg blockade. And it's the following. Supposing I have an atom over here at the origin that I excite up to one of these Rydberg levels that's got a big wave function. If I have a second atom very far away that I also excite up, I can just do that. And if they're far enough away, they don't really interact with each other. Okay. But if I try and excite the second atom closer into the first one, well, there's no state there. Because the atoms interact with each other, the energy of two Rydberg excited atoms lives on this molecular curve that scales as 1 over r to the 6th. And if the excitation rate, omega, is less than that shift, I won't get much excitation. And so there's going to be a blockade distance at which the interaction energy, V of r, is equal to the excitation rate, h bar omega, so that defines the blockade distance. And if I try and excite even closer in, I'll essentially get very close to 0 excitation. So this basically says I cannot have more than one Rydberg atom excited in a small region at a time. Okay, so that's the Rydberg blockade. And this blockade distance is not a physical quantity, it's a matching between the interaction strength and the rate of excitation. So it depends on the atomic levels. That interaction strength goes as n to the 11th in the van der Waals limit, and it also depends on how hard I try and drive the atoms. And so one can think about, so let me just add, one other nice feature of this is that if I'm working in this blockade limit where only one atom at a time can be excited, I can entangle the atoms using that method, but they're never simultaneously excited, and so they don't exert any force on each other. So they don't heat up. It's very quantum mechanical in that sense. So there's a couple different regimes within which you can think about this Rydberg blockade physics. So suppose I have an array of atoms. This is my qubit array. And I have a wide laser beam that I shine at all those atoms to excite them to the Rydberg level. And supposing that blockade distance that I mentioned is small compared to the spacing of the atoms, okay? That is, the atoms are further apart than this strong interaction distance. They'll all just get excited, okay? And that might be useful for making quantum sensors. And in fact, this company I work with, besides making computers, they make radio frequency sensors based on Rydberg atoms, quantum RF sensors, which is basically using this kind of idea. Then there's an intermediate regime where the blockade distance, which sort of limits, delineates the region over which you can only have one Rydberg atom, when that's comparable to the lattice spacing. If you try and excite all the atoms in that regime, they'll sort of self-organize into a pattern that minimizes the excess energy in their interactions, and you can get spatial symmetries emerging in a self-organized way. And this was shown in the Bloch group in Munich a decade plus ago in a very nice experiment. So this is the intermediate regime. And then you have this regime where the blockade distance is very large compared to the atomic spacing. And imagine that blockade distance covers the entire array. Then when I shine this laser light at the array, I get one Rydberg atom excited. However, it could be that one, it could be a different one, or it could be a different one, and so on. And if you think about that quantum mechanically as a coherent process, what I'm actually doing is transitioning all the atoms being in the ground state to this coherent superposition of one of the n atoms being in that excited state, and that's an n-qubit entangled state, so-called W state, that we get from a single pulse. So in a very natural, elegant way, you can create many-body entanglement using this Rydberg interaction. And for doing digital quantum computing, we'll mostly be interested in the two-atom limit, but I just want to emphasize that there's also sort of more general ways you can think about it. So I have a slide in a moment saying exactly how these gates work, but let me preview that. We're just showing you the process in entangling pairs of qubits using this Rydberg interaction. And so here I'm plotting the error of a 2-qubit CZ gate. So lower is better on this plot, that's lower error versus the year. These were the first experiments that were done here and in Paris. And then you can see a lot of progress here, where the very latest experiments are now in between 2 and 3 nines of fidelity. And now 4 different atomic species have shown better than 2 nines of fidelity, with the very best results being strontium, which has hit 99.7 fidelity. So lots of progress. What led to that progress? One, the atoms were made colder. The very first experiments had not so great laser cooling. These later experiments have colder atoms, so they're not moving around as much. There's less Doppler broadening. We developed better lasers, so the role of laser noise became better understood, and we used better lasers. And also the protocols, the way you entangle the atoms, were improved, and new protocols were developed. And so let me talk about that. Let me skip this slide. Come back to that later, maybe. So you can ask, with what fidelity is it in principle possible to entangle a pair of atoms using this Rydberg interaction? Okay. So the sort of general setting that I have 2 atoms, I'm going to excite them to Rydberg states, there's going to be some interaction, and then I'm going to bring them back down to the ground states, and I'm going to cross my fingers, twirl around a couple of times, pray, and hope that they get entangled. But I can ask, well, how well could that in principle work? And it turns out that there's a fundamental limit that's not hard to prove, which says, in principle, whatever protocol you come up with, how good could it be? And it's hidden in this old paper from Klaus Mulmer and others from 2007, who showed the following result. And I'm not actually going to derive it, but I'll just sketch for you what the result is. It says that I have 2 interacting particles. They could be Rydberg atoms, they could be molecules, they could be spins. But if I'm going to use transfer of my qubits to 2 interacting states that interact with a strength V, then in order to generate 1 unit of entanglement, and that's what a good CZ gate would do, the integrated population in those interacting states must satisfy this inequality. And that's derived by doing a Schmidt decomposition on the initial state, looking at the growth of the Schmidt coefficients over time during the gate, and relating that to the population in the interacting states. And you come up with this result that the integral over time for the duration of the gate of the population in the interacting states must be at least as large as 2 over V. Okay? It tells you how much integrated population you need to prepare 1 EBIT, or 1 unit of entanglement. And this piece of R, that's the one atom being in the interacting state, the other, or both. You do not need to have both atoms at the same time being in this interacting state. So this will work in Blockade limit. And if those states are decaying with lifetime tau, that decay leads to an error, and so you immediately find that the gate error is bounded below by 2 over V tau. So that's the fundamental limit. So then you can ask, well, so that's a limit, but it's not prescriptive. It doesn't tell you how to reach that limit. Can we achieve this scaling? So here's the original gate protocol that was introduced 25 years ago, and it involves 3 pulses, pi, 2 pi, pi. Okay? And the idea there is, what do I want to say about that? Well, so you put a pi pulse on the control qubit up to the Rydberg. You do a 2 pi on the target, up and back down, and then a pi again. And sort of the magic occurs when both atoms start in this one state, which is Rydberg coupled. If the first one's excited, then the blockade interaction shifts that level. This 2 pi does not happen, and so you do not get the the pi phase shift that would occur from going up and back down, and that gives you, turns out that gives you the entanglement. And you can show that the error scaling of this gate, where does the error come from? Well, you're spending some time in this Rydberg state that decays with lifetime tau. And so the amount of time you spend scales, or the error scales, is the amount of time you spend in that state times the decay rate, 1 over tau. So it scales as 1 over omega tau. So there's a, let's try that here, there's a scattering error, which goes like 1 over omega tau, because 1 over omega is the amount of time you spend in the Rydberg state up to some constants. And then because the interaction is strong and shifts this level away, it's not infinitely strong. So even if the first atom's excited, the second pulse still has some off-resonant coupling to that excited state. And so there's what I call a rotation error, which scales as omega squared over b squared. Right? If I go slower, then that off-resonant shift due to the interaction becomes more effective. If I go too fast, then I pick up more rotation error. So if I go very fast, I have small scattering error, but big rotation error. And if I go slow, I have small rotation error, but big scattering error. So you can just minimize the sum of those two terms to get an estimate for what your optimal Rabi frequency is. And if you do that and then add the errors together, you find this error scaling that's 1 over b tau to the 2/3, okay? Which is clearly not as good as, okay, I'm using b here, but it's the same as b, as 1 over b tau. Okay? So that original protocol doesn't saturate that bound. So, you know, can you do better? And sort of one of the big breakthroughs was a couple years ago, Guido Pupillo in Strasbourg introduced this time optimal protocol, which just drives both atoms with the same laser pulse and modulates the phase of the laser pulse in a way that the atoms go up, interact, acquire an interaction phase, and come back to the ground state as fast as possible with essentially no rotation error. And this has been the workhorse now for all of these high fidelity gates. And you know, I'd say assuming very low noise lasers and good environmental control and no technical unforeseen things, you know, I think fidelities beyond 4 nines are going to be possible, and we and others are working on it. The field's not there yet, but there's a path out there to get to very high fidelity with these gates, and it's exciting to see how long it's going to take. Okay, so that was kind of a quick summary. I could say a lot more. Let me stop there again and ask if there's any questions about gate interactions. All right, so let me go on then to architectures. Okay, so, you know, what do these systems look like? I was going to include some more lab pictures. I think I forgot. But anyway, one starts by doing laser cooling and making some cold atoms, and then having some trap array, either tweezer traps or bottle traps, and loading atoms into that array. And then you take a picture, and you'll find there's some filled sites and some empty sites, and then you have some other movable tweezers that grab atoms and move them around, and so you can do fun things like write physics using atoms or make Eiffel towers, whatever you want to do. But you're going to prepare a filled array, okay? So that's sort of the starting point for doing your quantum computation. Then you're going to do some internal state initialization using optical pumping, which I didn't talk about, but there's ways of shining laser beams at atoms to put them in one well-defined state. So called optical pumping. And then I'm going to run my quantum circuit, some 1 and 2 qubit gates, and implement my algorithm. And then I'm going to measure the results, and then I'm going to repeat that cycle. Yeah. And over some time scale, I'll also lose these atoms, so I may have to go back and and reload some missing sites and so on, but that's the basic idea. And so, what's been done in just the last couple of years, here in Madison, we did some small-scale demonstrations of multi-qubit entanglement and algorithms, including the quantum approximate optimization algorithm on just a handful of qubits. And then there's been this really very innovative work based on transport of atoms from the Lukin group, where they've worked with larger arrays and moved atoms around and showed that they can use that to implement long-range connectivity. Because even though these Rydberg interactions are long-range, they don't go out to 100 microns. And they're not going to get you from one side to the other side of a 1,000-qubit array. And with motion, you can go much further. And so this has been a very important development in the field of how you solve the connectivity challenge, which is really common to any qubit platform at some level. So just going back to this architecture for a moment, where we have stationary atoms and then are moving laser beams around to address different qubits and do gates. We've done a couple things with that over the years. We did this experiment showing GHZ states, phase estimation, and QAOA algorithm a few years ago. At Inflection, we've also been using that architecture and done a really good job of engineering of these tightly focused beams to push the gate fidelity up above 2 nines. They also did an experiment with logical qubits and generated logical Bell states, and it's some benchmarking of random circuits, and also a small-scale demonstration of an Anderson impurity model, and showed using error detecting small logical qubit codes, they could get better results than they had with the basic physical qubit implementation. So that's another result. And then the most recent result from the lab here, which is coming out on PRX Quantum, is an implementation of the variational quantum eigensolver for a certain many-body spin model. And this was kind of fun, where we took the laser beam motion we used here for addressing different atoms and combined it with some local atom motion within the circuit. And so you see that here. This is one of the circuits we ran for this variational quantum eigensolver. I'm not going to go into the details of the algorithm. And during the circuit, this is actually what's going on. The laser beams are flashing on and off at different positions, but also the atoms are being moved around to enable different atom pairs to be entangled. So there's a whole toolbox of different ways of implementing things with these atom arrays, and we're certainly just at the early days of figuring out the best approaches for really scaling these things up. So, and then this logical processor approach based on the atom motion, shown here. This is from last year from the Harvard group, where they have this sort of segmented region approach, where they're going to have logical qubits stored here, a reservoir of ancillas. They say they want to entangle this logical qubit with this one, then they're going to move them down to this entangling area, and then have a large Rydberg beam. And by having pairs of atoms that are spaced close together, but each pair is relatively far apart, so you can sort of entangle the pairs independently, but simultaneously, you can then turn on this large Rydberg beam if you have a powerful laser and entangle an entire logical gate at one time. This method, and for measurements, they have this additional zone here. So this is an architecture that people are looking at. You know, one of the questions here is, well, all this motion, how fast is that? And you know, how far can you push deep circuits based on motion? So there's a lot of trade-offs in this business. If you think about using surface code for logical qubits, then you only need nearest neighbor interactions for the surface code. But the code rate of the surface code is not good. It scales as 1 over the code distance squared. So if you want a very high performance, low logical error rates with the surface code, you need a lot of physical qubits. There's been a huge amount of activity in recent years with these new quantum low density parity check LDPC codes that have better code rates, reduced qubit counts, but they fundamentally require non-local interactions. And to a certain extent, you can implement those non-local interactions using these Ripper gates. And there's a couple of papers, one from us, one from a French group, showing that. The other option is atom transport for long-range connectivity, but it's relatively slow. So I'll show you a couple slides comparing some of the options. So here's a plot of interaction energy of, I think this was n equals 90 or 100 Rydberg states from 10 to 20 microns. And out at, say, 15 microns, I have about 4 or 5 megahertz of interaction, which is enough for a high-fidelity gate. So one can sort of take that and ask, could we do a logical gate between two surface code qubits without physically moving the atoms? Okay? I'm going to leave the atoms in place, and then I'm going to shine laser beams, say, between that atom and that atom, that atom and that atom, and so on and so forth, for all the pairs of data qubits. For codistance d, there'll be d squared such gates. And I can sort of make an assumption about the duration of my CZ gate, which for state-of-the-art time-optimal gates is a few hundred nanoseconds, and the time it takes to move my laser beams from here to here to here and so on. That depends on the technology, but we can also do that in about half a microsecond using acousto-optics. And so you can see the number of microseconds to perform a CZ gate between logical qubits. This is for a d equals 10 surface code patch, so 100 of those gate pairs. And so something maybe a little bit less than 100 microseconds. Okay. Then I might compare that with the approach based on atom motion. And I could think about moving my qubits over to some other region where I have a Rydberg beam. I could also think about just moving the data qubits in one logical qubit over to another logical qubit, and then arranging to have these pairs of closely spaced atoms, and then turn on some global Rydberg pulse that illuminates that patch there, and then move the atoms back. And then the time depends not so much on how long it takes for the Rydberg pulse, which is sub-microsecond, but how long it takes to do the motion back and forth. And one of the other things that's being developed in the last couple of years in this field is sort of transport techniques for how you move atoms rapidly without exciting their motion, without heating them up. And it turns out it's related to a quantity called jerk, which I hadn't known was a technical quantity. Jerk is the derivative of acceleration, or the third derivative of position with respect to time. And the amount of motional heating, so the vibrational quanta that the atoms will acquire during the motion, is related to how much jerk there is. And so people have looked at transport profiles that have constant jerk, where you have constant derivative of acceleration, and then you slow down to get to your destination. And other approaches with so-called minimal jerk profiles. So if you take a position trajectory that is a fifth-order polynomial, a function of time, you can choose the coefficients of that polynomial to minimize the jerk, so a minimal jerk profile. And the formula is not here, but if you do that, then you get a heating that depends on, for a fixed time, depends on the distance to the 1/3 power. So it's pretty efficient. It only scales to with the 1/3 power of the distance, how much heating you get. And so here I've plotted to move a certain distance and then back. These are plots of how long it takes, how much time for the motion, and how much motional heating I acquire. And if I'm willing to accept a lot of heating, I can go faster. And if I want less heating, it'll take longer. If the atoms are spaced by 5 microns, and it's a distance 10 code, I need to move about 50 microns. And so it's going to take a couple hundred microseconds to have, say, a tenth of a motional quanta excitation. And that's not bad if you're just doing a couple gate operations. If you think about really doing something serious with 1 million gate operations, you will have boiled your atom out of the trap. So you're going to have to recool along the way, and that sort of gets right to the frontier of developments with this approach, which is how do you run deep circuits with the information encoded in the spins and then actually recool the atomic motion along the way without destroying the quantum information in the spin state. Turns out there's ways of doing that. And that's really one of the frontiers of development right now. So there's these different options. Really, what one needs to figure out if you're serious about not just doing the physics, but engineering a quantum computer, is to think about design from a full stack perspective. That is, you have to think about what algorithm do I want to run, what error correcting code am I going to use, what physical tools am I going to employ to implement what I want to do. And so you need to come up with a full stack design and a compiler. And there's now lots of papers appearing all the time from physicists collaborating with computer scientists to figure out these architectures. And again, I'll say it's early days in this area to really go from, we did a fun physics experiment, to we're building a quantum computer that you can use to solve the problem. Okay. So, what are the outstanding challenges? One of them is measurements. I didn't say much about how the measurements work, but let's see, did I have another slide here? Yeah, okay. So here's a slide about measurements. So these gate operations are microsecond time scale. 1 qubit gates around a microsecond or so, a couple microseconds. If they're microwave, we can replace the microwaves with optical Raman. They can be sub-microsecond. The Rydberg gates are sub-microsecond. They're fast. The measurements rely on light scattering, where we choose a laser wavelength or frequency that interacts with one of the qubit states but not the other state, so we get state-dependent light scattering. The measurements tend to be very slow. And so here's a plot of integration time or measurement time versus the fidelity of the measurements. And here I'm plotting what I call a generalized fidelity, which is the fidelity with which one can distinguish the two qubit states times the fidelity with which the atom is still there after the measurement. Because the measurements give some amount of heating in general, and so I might kick the atom out of the trap. So this is the state detection fidelity times 1 minus the probability of loss, so kind of a generalized fidelity. And we'd like to be down here, very high fidelity and very fast, but there's no data down there. And so I've color-coded, again, the different atomic species. There are very high fidelity measurements that have been achieved in strontium and cesium. They're pretty slow, a couple hundred milliseconds. So 5 orders of magnitude slower than the gates. Let me repeat that, 5 orders of magnitude slower. Then there's measurements which have been as fast as 150 microseconds, but they're pretty low fidelity. And surface code threshold is right about here. So that's an open challenge. We're actively working on a method that might get us down here, but we're working on it. Let me say, we have some good ideas, I think. So measurements is one challenge on this platform. We're at 99.7 for the best entangling gate fidelities. That needs to be improved further. I mentioned that one of the limits to really scaling up is the beam scanning technology. People are working on that also. And just generally, we need to figure out what's the right architecture to really make these things possible. And so let me summarize. Rydberg atoms are nice because they sort of combine isolation and control in one system. These atomic qubits are super well isolated from the environment. Yet we can control them by exciting them to Rydberg states, having strong interactions, and then bringing them back down to the ground state. Being lots of progress, there's still lots of challenges, but plenty of good ideas how to proceed. From my perspective, I would say we're still at a very early stage for development of these these quantum computers. And I think that's true for not just for neutral atoms, but for all the approaches. You know, this was a vision of a computer 150 years ago, right? A mechanical computer, which actually was not built until after Babbage passed away. This is our current machine that you'll see up in the lab. I'd say it's pretty much as primitive as that thing, but interesting nonetheless. So let me stop there. We can take a few questions. There's one. There's Jamie.
All right, so you don't have to go back to the slide, 'cause it's from the beginning. That's an architecture question. So I'm curious, like you talked towards the beginning about like 3 different regimes, and when you have that kind of river blockade, like you'll just kind of almost seems like randomly, it'll be assigned to like one of those atoms.
Mm-hmm.
So is there any way to control that, or is it pretty random?
Well, you can implement multi-qubit entangling operations in a very controlled fashion by structuring your light to interact with certain atoms or doing some position-dependent detuning of the atoms. So you might be interested in the randomness, but for circuits, you might want to have many qubit interactions that are controlled, and yeah, that's possible. And then the trade-off is, does that work as well as just doing a sequence of, say, 2 qubit interactions? Depends.
Can I ask a question? About the grids that you have, where you load the atoms into. So, on the one hand, for analog simulations, but also potentially to increase the connectivity for digital quantum computation. What can you do? Can you, I mean, when they do analog simulations, they just load this square lattices in a certain manner to get a certain connectivity. Is that what's happening? Or a triangle lattice is also possible. Then also you have a coordination number of 6, which is maybe advantageous even for digital computation.
Yeah, we can do sort of arbitrary patterns, and I didn't mention the analog simulation approach, which is a whole other part of this Rydberg physics. And in fact, this Rydberg interactions and optical excitation maps in a very natural way onto the transverse Ising model. So you can do these Ising simulations using Rydberg arrays. We can do square lattices, triangular, disordered lattices, whatever you like. It's all possible.
So Mark, you mentioned when you load lots of items in a track, you mentioned that we don't have technology that would allow us to individualize and solve items, so there are limitations there. So who works on that specific part of the problem to improve that? And is it yet at the stage of some fundamental issues, or we know what to do, but we just need to get it done?
Yeah, that's a good question. So academic groups work on that. So my group has published an idea for how to do fast addressing of large atom arrays by combining 2 different existing technologies. So we have acousto-optics, which are fast, not so many degrees of freedom, and we have liquid crystal spatial light modulators that are slow, but many degrees of freedom. Turns out you can put those together and sort of get the best of both worlds. So that's one way of thinking about it. Some companies are developing integrated photonic devices where you sort of have these optical waveguides. It's sort of like the kind of things you see in what PsiQuantum's doing, not in terms of qubits encoded in photons, but using optical waveguides as a way of distributing light, and then having integrated modulators, so you can build systems where you have 1 million modulators to let you, and then you just image that onto the atom array, and so you have this complete control. Requires a lot of laser power, requires fabrication, it's expensive, so companies are investing in that kind of thing. Yeah. And I think we'll see progress, but it's going to be a few years.
So that's time period from like 2010 to 2022, like from the first two decades of the circuits. Were there any like kind of interesting or like what were kind of the last things to get solved towards getting the circuit in 2022, and then like were there also some like kind of dead ends or like maybe
Sure.
some proposals that didn't quite work out?
Yeah, I think a couple things happened. One, this area with Newfoundland was a very small field for a number of years. We were working on it here. There was a group in France, the Prof group, and basically no one else. I mean, it was like almost no one was working on this because we showed this, you could do this gate in 2010, but it was pretty low fidelity, and a lot of people didn't really believe in it. One of the big advances was this rearrangement, which was Korea, Harvard, and France in 2016, which let you make these larger arrays that were fully occupied. And then you could really think about doing circuits. So there was the rearrangement, understanding of what was limiting fidelity, which was sort of laser noise and suboptimal protocols, and then finding solutions to those and pushing to high fidelity. And now it's a very active area where I'd almost say there's too many groups working on this right now.
Maybe ask another question. Can you briefly elaborate again what's the advantage of a bottle as compared to a tweezer? Maybe
Yeah. So I'll scroll back while I'm talking. The tweezer traps trap the atom at the maximum of the light intensity. Okay. Let's see here. The bottle traps trap the atom where it's dark. And in addition, for alkali atoms, you can trap the Rydberg state here. Where if you put the Rydberg state in this trap, it actually repels the Rydberg state. It's a little bit different story for the alkaline earth, the 2 electron atoms, where you can trap ground and Rydberg state in the tweezer trap. But the advantage is you can trap ground and Rydberg state for the alkalis using the using the bottle traps. Right there. Yeah. That's the advantage. The optics is a little bit more complicated, so it's been less popular. Actually, I'll show you a slide I skipped over. I can take one more minute. This is a collaboration with the CATS group in engineering here, where we fabricated a mask that produced both bottle traps and tweezer traps interleaved. And so we used one wavelength of trapping light that was blue for cesium and red for rubidium. And so we actually could trap cesium and rubidium in an interleaved pattern. We want to use this for surface code in a very, I'd say, elegant way using a single trapping wavelength, where the cesium only sit in these spots and the rubidium only sit in those spots.
and then, sorry, and then let's say green is the auxiliary qubit to make dirty checks for the...
Yeah, so say cesium could be data, and then this green rubidium, this is false coloring, but it could be ancillas for verification. Yeah, so we're actually building another one of these upstairs right now.
Okay, so no more questions. Let's first thank Mark. And then please get ready for the picture. Let's start here. Let's see if Sarah is outside.